Okay, so final video for chapter 8. We're going to look at the likelihood ratio test if one or more of our hypotheses are not simple, if they're composite. Try and pause, copy down the result, and then press play. This is all the results. All right, so we have the likelihood ratio test if H sub 0, our null hypothesis, and our alternate hypothesis were both simple, okay? So now, what do we do otherwise? So what does it mean to be a composite hypothesis? Well, let's say our population was normal with an unknown mean, but a known variance, okay? And if H naught is mu equals 8, that's a simple hypothesis. If mu equals 8, you know the entire population. The alternate hypothesis is mu is not 8. Maybe mu is less than 8. If you know that mu is less than 8, you don't know everything about the population. Maybe mu is 7, maybe it's 5. Who knows? It doesn't tell you everything about the population, so it's composite. So in this example, H naught is a simple hypothesis, but the alternate hypothesis is composite, okay? So what do? Well, let's let capital sigma denote the set of all possible values for the population parameter theta, which was mu in this case. And let capital sigma sub 0 denote the subset satisfying the null hypothesis, okay? So that's if the null hypothesis was composite as well. In our little pseudo example up here, capital sigma sub 0 would just be the number 8, the set consisting of the number 8, okay? All right, so in other words, the null hypothesis is that our parameter is in this set versus the alternate hypothesis is that our parameter is in the universal set, the set of all possible values, but not in capital sigma sub 0. It's not in the null hypothesis. Okay, having done that, we're going to set up our test statistic for the likelihood ratio test. We call it T of X. It's the maximum of the likelihood of the data under any theta hat, which is in capital sigma sub 0. So this is the maximum likelihood given that theta hat came from H sub 0, right? And then we're going to divide it by something slightly interesting. It's the maximum of the likelihood of our data X under any parameter theta hat, including the ones in the null hypothesis, right? So we don't just stick with the alternate hypothesis options in the denominator here. We take all possible ones. And honestly, if it turns out that the maximum likelihood comes from a theta hat from our null hypothesis, from capital sigma sub 0, then this fraction would equal 1. And that's not going to be less than a C. So it's not going to cause us to reject the null hypothesis, which it shouldn't, because the maximum likelihood came from the null hypothesis set. So it doesn't actually matter that our denominator is looking at things outside of the alternate hypothesis, okay? So we calculate T, and then as with the other likelihood ratio test, we're going to reject the null hypothesis when this statistic is less than or equal to C for some C between 0 and 1, okay? I mean, this fraction can only ever be between 0 and 1 because it's a difference of a ratio of likelihoods. Okay, and further, in this test, we can actually figure out p-values as well. If we observe t of little x, then the p-value is the probability that t of any x being less than or equal to t of little x. So that's the as extreme or more extreme. The more extreme would be smaller likelihood ratio. All right. So the next 3 panels are going to be a single example, and it's kind of a challenging example. So all I would say is occasionally we do examples where you just have to hold on to your hat and try and stick with it as best you can and play it over and over again until it starts to sink in, because these are involved problems. So pause, copy. All right, so here's our setup. I've got a random sample of n data points from a normal population whose mean I don't know, but whose variance and standard deviation is 1. Now, since I know the variance is 1, I know the PDF, the PMF, the PDF of a normal distribution. 1 over the square root of 2 pi times standard deviation times e to the negative x minus mu squared times 2 times variance. Okay, so there's my PDF. It'll crop up here. Okay. Now, my null hypothesis is that the mean is 8, and my alternate hypothesis is that the mean is less than 8. So a simple hypothesis, a composite hypothesis. And the setup's going to be, I'd like to have a significance level of 5%. So I'm okay if I mistakenly reject the null hypothesis 5% of the time. I've been given 4 data points, and there they are, 7, 7, 6.6, and 6. Okay? And you'll note they're all less than 8, which might suggest a mean of 8 doesn't seem likely. Because if the mean was 8 and I give you 4 random samples, you'd expect about half of them to be less than 8 and half of them to be greater than 8, since the normal distribution is symmetric, centered at 8 under the null hypothesis. Okay. All right. Well, so our goal is to determine whether or not to reject the null hypothesis via the likelihood ratio test. So what we're going to do is we're going to spend a lot of time figuring out a critical region. Okay. All right. First off, the likelihood of any mean mu, given that I have 4 data points, is going to be the product of those 4 PMFs, 1 for each data point multiplied together. So 1 over the square root of 2 pi times 1 will be multiplied by itself 4 times. And then those e's, 4 of them multiplied together, I can mush the exponents together, factor out the negative 1/2, and I just have the sum of the xi minus mu quantity squares. Okay, so that just is going to simplify my algebra later on. So for example, the simple hypothesis in the numerator, if I want to maximize the likelihood under the null hypothesis says mu equals 8. That's it. So to maximize it, I'll say mu equals 8. So the likelihood of mu equaling 8, according to this formula, is just replace the mu's with 8s and insert the x value, 7, 7, 6.66. Crank it out, and I get 0.000473. Okay. Now, the denominator is the maximum possible likelihood that's out there for any value of mu. And what we know from our maximum likelihood estimator work is that the sample mean maximizes the likelihood. So our sample mean is 6.65, and so the likelihood function is maximized at 6.65. Okay, I mean, that's we showed that result in chapter 6. I don't know, whenever we did maximum likelihood work. Okay, all right, so let's calculate the likelihood of mu equaling 6.65. So it's going to be the exact same work up here, except the 8s are going to be 6.65s, and that cranks out to be 0.0181. Okay. T of x is then the ratio of those two, which is 0.026, and that's small. That's saying it seems far more likely, or the denominator is far larger than the numerator, so the denominator is far more likely than the numerator is. That's evidence to reject h sub 0, okay? Okay, so, but now that we got that, let's go seek the critical region for x, okay? No, that way. Okay. So we're going to go for the critical region now. So why don't you, and I'm going to back away from my specific data and go a bit more general to get that critical region. So I need to pause, copy, and play. All right. So backing up a step, if I remove the actual values of x1 through x4, what I had for t of x was the likelihood at mu equals 8 divided by the likelihood at mu equals x bar, because we know that maximizes the likelihood function. And I'm going to simplify that. So the 1 over root 2 pi to the 4th cancel, and then I can take this top power minus this bottom power. Both have a negative 1/2, which I can factor out. And I think that leaves me with, since I factored the negative out, I think I get that first sum minus this bottom summation minus this top summation, if you just check the algebra there, okay? Then I FOILed out all these squareds and expanded all 4 of them together and did a bunch of algebra. and that exponent simplified to be the negative 1/2, and then 4 copies of the square of x bar minus 8, okay? Bunch of algebra there. If it's a rainy day, crank through it. Just have yourself an algebraic party, okay? Anyway, so we get to this. And then the likelihood ratio test tells us we're going to reject H0 when this value, the simplified value of T of x bar is less than or equal to some C, okay? All right, and I would just point out that if x bar happened to equal 8, then the numerator and the denominator are the same, and it's 1, and we would not reject the null hypothesis. Okay, that's a really large value of T of x. It's not less than or equal to a C. It's the largest value of T of x possible, okay? All right, so to reject the null hypothesis, we need x bar to be less than 8. And via algebra, we need this guy to be greater than or equal to this thing. So where did this come from? Well, if I solve this inequality for x bar minus 8, I'm going to take the natural log of both sides. That's where the natural log of C came from. I'm going to, what am I going to do? I'm going to multiply by negative 2/4 to kill that thing off. And that's going to flip my inequality. And then when I take the square root of both sides, I get an absolute value here and the square root there. Okay, so I just did some algebra on that inequality to get to here. And then since I know that x bar is less than 8, this absolute value is simply 8 minus x bar. And if I solve for x bar, I can send x bar to this side, the square root to that side, and I get that inequality. And this monstrosity, I'm just going to call C2. Okay. So here's my critical region. I'm going to reject if x bar is less than or equal to 8 minus some C2. So let's bring that alpha into play and figure out that C2. We're told to let alpha be 5%. And that's the probability that I reject H0, given that H0 is correct. I now know I'm going to reject H0 when x bar is less than or equal to 8 minus C2. And H0 correct means mu is equal to 8. All right, so what does mu equal 8 mean? Well, it means that my x sub i's were normally distributed with mu equals 8 and a variance equals 1. Well, if that's the case, then x bar is normally distributed with the same mean, but the variance is scaled down by 4, right? That's how we calculate the variance of x bar if we knew the variance of each x sub I. And if that's how x bar is distributed, I'm now going to standardize, get this into standard normal form. So I'm going to subtract 8 from both sides and divide by my standard deviation of 1/√4, which is 1/2. That's going to create a z right there. So that's all a z variable, standard normal variable. So this is just sigma of negative C2 divided by 1/2. And that's just negative 2 times C2, okay? So I have 0.05 is equal to this value. Last panel, big conclusion. Okay, that's where we were in the previous panel. Why don't you pause, copy? Okay, so I want this value to have 5% of the area or probability to the left of it. So I looked at my standard normal table, and the 0.95 value, 0.95 probability, or 95% of the area to the left of it, occurred at positive 1.644. Since N01 symmetric, 5% of the value to the left is at negative 1.644, solving for C2. Thus, my critical region at alpha equals 0.05 is the set of all sample means in which the sample mean is less than or equal to 8 minus 1.644/2. That value is T sub 2, which turns out to be 7.178. Now, our data had an x bar 6.65, which is definitely less than 7.178. So we would reject H0 and conclude that there's statistically significant evidence to support mu being less than 8. Okay. Now, you might be concerned about, like, hey, why was the first likelihood ratio test with simple hypotheses? Why did we have T of x strictly less than C, and here we have less than or equal to C? A, it could have been I screwed up and it should have been less than or equal to C for both of them. Check the book. B, it doesn't much matter, right? Whatever you calculate it to be is being forced upon, well, the value of alpha is driving the ship. So whether you say T of x is less than C or less than or equal to C, once you plug in the 0.05, you're going to solve and get a similar critical region, identical critical region. So it's not an important issue having T of x less than C or less than or equal to C. All right, so that concludes chapter 8.